Good morning. I'm going to tell you about triangulations, and this is a topic that might fit into one of our third or fourth year algorithms courses. So I have some pictures of triangulations here. And let me just spend a moment saying how I'm doing things. For most of the 25 years I've been here, I've taught on the blackboard. And in the last 10 years, I've usually given students the option. I'll do one lecture on the blackboard, I'll do one lecture with slides, and I'll take a vote. How would you like me to continue the rest of the term? And they've always been voting for the blackboard, which is lucky for me, because that's what I've prepared anyway. But I don't steer the vote one way or the other. And I think the reason they choose this is because a lot of the courses I'm teaching involve proofs and going through things step by step. And it slows you down to work on the blackboard, and you're sort of mentally engaged. So I do like doing that. On the other hand, I love showing pictures. So lately what I've been trying is a mix of the two. So I have some slides that I've made in a program called Curio on the Mac, and I'm presenting them on an iPad. I've listed the app that I'm using there. And then what I do, because what goes by on the slides goes by pretty quickly, I put that up as PDF afterwards. So the students who are trying to take notes can take notes of what I put on the board, but the stuff that's on the slides, they get for free. So let me start by defining what is a triangulation. Unlike those pictures I showed you at the beginning, we're going to just triangulate simple polygons, and we're not going to use extra vertices in the middle, extra points in the middle. So first, just to say a little bit, what is a polygon? We looked at this before, but just to remind you of some things that are not simple polygons. We're not allowing that our line segments will come and cross each other. So this is not a simple polygon. Also, we don't allow that one vertex comes up and touches on a line. This is also not a simple polygon. So something like this is, and what we're relying on is, remember I mentioned the Jordan curve theorem that says every simple polygon has an inside and an outside. That's a very fundamental and somewhat hard to prove result, but we take it for granted all the time. And indeed today we're going to take that for granted. See if you can tell where I do that. OK, so that's what we have, a polygon. And then we need to talk about these chords. These are line segments inside the polygon that go between two vertices. So that's what a chord is. And let me also draw a picture of some things that are not chords, just to emphasize. So if I have some kind of polygon, this, for example, is not a chord. It goes between two vertices, but it steps outside the polygon. Also, this is not a chord. It doesn't cut any of the polygon edges, but it's entirely outside. OK, so the chords are the things inside. Now, what else is this definition saying? We want to add non-crossing chords. So what would crossing chords be? Just when they cross each other is what I mean. So here's an even simpler polygon. This chord and this chord cross each other. So I don't want that. I'm going to add a set of non-crossing chords until we partition the polygon into triangles, is what the definition says. So can someone suggest another chord that we would add in this picture? Yeah, 2 to 6 would be an example that cuts off another. I guess I don't want to make it too big. I could do this, this, this. I can't go from here to here, but I can go like this and this. And now we have our triangulation. Now, I've written this definition in a slightly non-standard way, a sort of algorithmic way rather than a math way. The typical math way of saying it would be that we have a maximal set of non-crossing chords. What does maximal mean? It just means that we can't add any more. So I've just said it in a slightly, you do this, rather than using the word maximal. But it is the same thing. The other slightly puzzling thing about this definition is that it says we add these chords until we get triangles. And you might say, well, how do I know that I can do that? Why can you just keep adding chords until you get triangles? We've studied matching algorithms, for example, and if you want to pair up vertices in a graph, it's not true that you can just say, oh, I'll take this pair, this pair, this pair, and hope to match them all up. Sometimes it's not possible. Sometimes it is possible, but if you do this sort of obvious method, it won't get you there. Maximal is not the same as maximum. So the danger with this is that we might add some chord that's somehow a mistake, and it prevents us from getting all the way to triangles. So let's take a vote. How many people think that danger can arise here? And yeah, so I've been convincing enough about saying that there might be a problem, eh? How many people think this danger won't arise at all? Well, the rest of you are non-committal here, non-committal. Okay, so we're going to look at a proof that every polygon can be triangulated. That's a very fundamental first result. And the basic idea is that, notice once we pick one chord, we've divided our polygon into two. So all we need to say is that there is a chord in any polygon, right? Because then we could use induction and say, okay, one chord divides me in two, and I have two smaller polygons now. Each of those can be triangulated. So our crucial lemma is going to be that every polygon with more than 3 vertices has a chord. What about the polygons with 3 vertices? Well, they're triangles, they're triangulated already. We don't need to do anything. That's going to be our base case of the induction, right? So let's look at the proof of this lemma. Now, one thing you might notice about this triangulation over here is we're trying to find a chord, but here there are some special chords, some that cut off a single triangle of the polygon, right? So as opposed to this chord, which just cuts the polygon into 2 non-triangular pieces, bigger than triangles. But this one cuts off what's called an ear. So you might think, and this one also cuts off an ear, right? But none of these other ones do. And I do not have a fancy enough example here to show a triangle. Here, I'm going to expand my polygon a little bit. So now this one is also an ear. And I can have triangles that just use one edge of the polygon. And I can have triangles like this one I just snuck in, that don't use any edges of the polygon. The difference about ears is they use 2 edges of the polygon. So you might think, well, we could strengthen this lemma and try to show that there's always an ear. And in fact, this is called Meister's 2 ears theorem. He proves that in any polygon, there's always at least 2 ears. Now, that's a stronger statement, and it's actually a little harder to prove. So we're not going to tackle our lemma that way. Now, on the other hand, this, starting with, these are called convex angles. And this one, for example, is a reflex angle, larger than 180 degrees, larger than pi. Starting with a convex angle seems like a promising thing. So in fact, that is how this proof will start out. Now you might say, how do I know that every polygon has a convex angle? Well, we're going to sort of escape from that by, say, consider the leftmost, and in the case of ties, topmost vertex of our polygon. Okay, so we're finding the line that first touches the polygon, looking at a vertex there. If there's more than one, we're taking this topmost one. Okay, let's call that V. Now, it's going to have 2 neighbors on the polygon boundary, but that's going to make a convex angle no matter what, right? Its top neighbor can't be above it. It has to be strictly to the right. The one below might be on this line, but in any case, we have a convex angle here. So we're going to start our proof here. Here's the inside of the polygon. So there's a convex angle at V. And we're going to look at its neighbors, U and W. So U is up here and W is down here. Now, what shall we try for our chord? The obvious thing is to try UW. And if that's a chord, we're done, right? So if UW is a chord, we're done. So we have to consider the case when UW is not a chord. And what does that mean? It steps outside the polygon somewhere. So some part of the polygon steps inside here. Okay? Now it's easy enough to see that then there has to actually be a vertex that has stepped inside. And what we want to find then is some vertex x such that Vx is a chord. That's the plan of how this proof is going to go. So else find x inside the triangle UVW such that we get a chord Vx. Okay, I think that Vx might be hidden from those of you at that side there. But. So any suggestions as to how I might pick vertex x? I might have a more complicated example like this, right? Where this would be the wrong x to choose because now Vx is not a chord. There's lots of things that will work. Yeah? The leftmost? The leftmost one. That is an excellent idea, the leftmost one. Any other candidates? Where's my brush? Thanks for the chalk. The closest x. That's also an excellent idea. There are published proofs that use both these ideas. They are both wrong. So as an exercise, show that these do not work. And the thing that will, yeah, question?
Can you choose any x that decreases the area from Vx? Because the thing is finite, so if at every step you decrease the area.
So choose. Yeah, we could try something iterative where, maybe we try UV and this x and we say, I don't know how we would exactly proceed there, but there's probably a way to do something like that. But there is, in fact, a way to just pick our x in the first place. So that's what I'll try to show you. So if we take this line, UW, and we start off placing a parallel line through V, and we sweep it towards UW, while staying inside the polygon. We're not going to get all the way there, right? Because UW was not a chord. It's going to stop somewhere. And where it stops, it has to be a vertex. And that is going to be our choice for x. So this will be our x. OK. So sweep a line parallel to UW from V towards UW. The first point outside the polygon is the vertex V. X. And why is Vx a chord now? Well, because its whole length is inside the polygon by our method of how we swept things. So that's the proof of this lemma. And from that lemma, we can prove the theorem by induction. I will not, if I had time, I would show the details. But I'm not used to preparing 15-minute lectures. Okay, so as an exercise, I'd invite you to prove the following more general result, that if we have a set of points and some non-crossing line segments, so a polygon would be a special case of this, show that we can always complete that to a triangulation. So here's an example of doing that. And a challenging thing is to show that if we go up to 3 dimensions, things don't work out. You can find a 3-dimensional polyhedron that cannot be partitioned into tetrahedra just by using the original vertices. That's a very curious and interesting example. Okay, so I was going to talk a little bit about the number of chords and triangles in a triangulation. However, I think there's some more interesting things I did want to say. There's also interesting things about the number of triangulations, but more crucial to our course, which is an algorithms course, is to talk about algorithms to triangulate a polygon. So this proof that we gave does give us an algorithm. It was a very algorithmic method, right? Find a chord and then recurse. And an obvious implementation of that will take order n to the 4th. And here on this slide, I have exercises that invite you to improve that. And again, I think I will skip those details. What I would, in an actual lecture, point out is that there is a more efficient algorithm, and that's a thing we would spend more time on. There's an n log n algorithm, the first step of which is to do something that doesn't seem related to triangulations, which is to cut the polygon via vertical lines into trapezoids. So more details on that next day. And what I'll mention at the end is one of the really more curious things about algorithms, which is that there is an optimal algorithm, an algorithm that takes order n time for an n-vertex polygon. This is a tour de force of Bernard Chazel's from 1991, after a decade at least of attempts by various researchers. So it's a very well-cited paper. This, by the way, comes from Google Scholar, which if you're interested in doing a little bit of research, Google Scholar is your friend. Learn about it. But this algorithm is so complicated that no one has ever implemented it. So it boggles the mind to think that, you know, we study algorithms, we think, oh, linear running time, that's got to be the best algorithm. But it's not if you can't use it, if you can't implement it. And you know, glance at this paper and see how long it is and see why it is that people haven't been able to implement it. So it's an important result from a theoretical perspective because this triangulation is used as a stepping point for many other algorithms, like finding shortest paths in a polygon. People say, oh, first triangulate the polygon. This can be done in linear time. But in practice, you don't do it in linear time. You look for randomized or other techniques that behave well in practice. Okay. What I expect you to know or do from this very short lecture is know the definition of a triangulation and be able to prove some basic properties of triangulation, proofs by induction, as we did an example, and to understand the obvious algorithm to triangulate a polygon. And next, we would continue with the more efficient n log n practical algorithm and talk about some special triangulations. So, and just to say, this is material that I have taught occasionally over the years, but there is a very recent book that has beautiful exposition of this in case anyone's curious. And this would be the book. And to end, I have one last thing. Often when I teach, I ask students questions, and sometimes I'm really waiting for an answer, and sometimes I'm just asking a question and I just sort of continue and answer it. Now, I think there's value in doing the second thing. And what I want to ask you, and I wouldn't get an honest answer from students necessarily, is when I asked those questions where I just sort of went on, did you think about the answer? How many people did? Okay, cool. Yeah, thank you. That's it.